Hello and welcome to ICDD's InSession webinars. Soon you will hear ICDD's former Executive Director Tim Fawcett and ICDD's Executive Director Tom Blanton presenting Setting Up Your Lab. Please remember to visit icdd.com for information on future free webinars, educational events, product information, and to purchase ICDD's databases and software.
Okay, today we're going to talk about setting up your lab and the type of diffractometer database and software that you may need. And here we have a photo of a typical lab. We have 3 diffractometers. You can see some complementary techniques, a microscope over here, a microanalysis area over here, and plenty of room for people to do their analyses. But today we'll be talking more about this type of lab where we also are preparing samples, and you can see people with mortars and pestles and sieves and specimen holders for the equipment, and we'll be getting into both these aspects. Now we're going to talk about specimen preparation and complementary techniques, diffractometer tips, and database and software options. And each of these subjects we'll talk for about 10 or 15 minutes on. Wanted to bring that up because all these 4 topics are actually things that we teach in our classes, and we usually spend an hour, if not more. Specimen prep can often go 4 to 6 hours, but we're going to cover them very quickly today. So this particular talk will be very application focused. And if you want to get the theory and how it blends in with the application, I would recommend you go to the ICD clinics, which is a more balanced type presentation. And the 2 speakers today are myself and Tom. We both started out in industry, and we've set up diffraction laboratories in industry, myself at Dow Chemical and Tom at Eastman Kodak. Also, since we've both been an executive director, we've had the pleasure of going to some of the best laboratories around the world as part of conferences and giving presentations. And so I don't like to say we're old. I will say instead that we're highly experienced. So we're very experienced in this particular subject matter. If you look at people that belong to the ICDD and look at what kind of labs they are in, you'll find material science, physics, chemistry, and geology is quite frequent, as well as analytical science and geology. But there's a huge diversity. There's also medical schools, pharmaceuticals, mineralogy, astronomy, earth sciences, astrosciences, glass labs, coal labs, forensic sciences. So one of the things we're going to do today is we're going to try to talk to you and present things that are used in all these laboratories, every single one of them, and then give you an idea of when they may deviate and be more specific to a more specific field of science. We're also going to describe samples and specimens. Usually if we're talking about a sample, this is what somebody gives to you to analyze, like a piece of concrete or a pipe clog or a mineral. And when we talk about a specimen, this is usually what we present to the diffractometer, which means we've gone through our preparation steps, we've made a fine powder. In some cases, like the non-destructive evaluation analysis of this Roman coin, the sample is the specimen. Now, X-ray powder diffraction operates under the assumption that the sample is randomly arranged and we have a statistically significant number of each plane in the crystal structure that's in the proper orientation. And the proper orientation is very important. That is, the proper orientation is a result of Bragg's law, where we get diffraction and we get constructive interference when we are the uniform spacing apart between our inner atomic layers, and that comes out at a specific angle. If we look at a transmission experiment, that means certain one of these crystals will be in a position to diffract to satisfy Bragg's law. That's where you get a peak where the waves reinforce each other, constructive interference, and that'll be at a specific 2 theta. But in a transmission experiment, your diffraction actually comes out in a cone. Every point along the cone is at that same 2 theta, but you do have a cone coming out from the sample. Now there'll be another cone where you'll be sampling a different atomic plane that will require a different angle, and that's represented by this green circle, and these are called Debye-Scherer rings. If we're in a reflection geometry, we get the top half of this cone, and we go off the surface. Now, this is shown schematically in a great diagram that was generated by Bob He at Bruker Analytical. And he shows that if you have this randomly oriented polycrystalline sample, you'll get these uniform cones coming out from the sample. If you have a single crystal, so you have one crystal, very specific orientation, you get a series of points. Now, if you have something in between, or you might have a layered structure where the materials are not random, they're in specific three-dimensional orientations, you might get arcs, or in a case like this, you might get multiple points because you have multiple large crystals, but not a random orientation. So this just shows some of these representations on a real two-dimensional detector. Here we have our perfect cones coming out. Here we have arcs, and here we have multiple single crystals, but not sufficient for truly random orientation. Now, if we take our strip detector and we go along one particular dimension, like the middle dimension here, and then we look at the peaks that we cross, you'll see something like the conventional pattern that we all get. And if we're in the random orientation spot, it doesn't really matter if we go in this direction, or this direction, we'll get the exact same pattern that's characteristic of the despacings of the material. And this is how we identify materials. You can see that if we have something textured, though, we may come along to the same area, and maybe for one of the reflections, there's no intensity, and for another reflection, there's an enormous amount of intensity. So you have irreproducible intensity. So what we want to do is we want to get this and avoid this. So we have randomly oriented particles that we want, and we want a statistically significant number of particles. And a question you might want to ask is there a magic size? And the answer is there is, and it's about a micron. So one of the first steps we'll do in all our labs, we need to grind our samples, and we need to grind them to a fine powder. And a 1 micron is a very, very fine dust. Now, why do we say that? I'm going to give you very quickly on the theory. It's actually quite complex. But just to give you a short rundown, you need to have a sampling volume. So we're going to take this cup, and the cup will have a particular volume. And then you can calculate, if you have a certain particle size, how many particles are in that volume. And we're talking about millions if we're at 10 microns and billions if we're at 1 micron. So this is why getting your sizes down to the micron range is so critical. You can see how the numbers dramatically change as we go from 40 to 1. And then we have to have them in a specific position to satisfy Bragg's law, and the detector at a specific point along the Ewald sphere. And this is shown by a certain vector coming out. And if we do that geometric constraint, we say of these 60,000 particles, we only have 12 in position to diffract at a particular point. And if we have 10, we're at 760, and at 1, we're at 38,000. Now 38,000, we're now starting to get to the point where if you wanted a 1% error in all your peak intensities, you're approaching statistical significance of that 1%. Now, one thing that helps us out all the time, but is an unknown factor in our experiments, is we talked about particles here, but what's really important is the crystallites. And usually crystallites are a subunit of the particle. And sometimes we get lucky. There's usually multiple crystallites in a particle. There's a multiplication factor here. So many times if we get down to 10 microns, say if there's 100 of these crystallites in a particle, we'll get sufficient number of particles to satisfy the equation. But you usually don't know this in advance. And that's why I have this coin, and I said, get lucky. It turns out that the corrosion on the coin is nanoparticulate. We identified that and measured it. It turns out that the metals used in the construction of the coin, this is an old bronze Roman coin that was cast, and we know it was cast, and the particles were a very fine microstructure and they're randomly oriented. So in this particular case, we could get a perfectly good diffraction pattern off this coin without any sample prep, but that is rare. Most of the time, if you're looking, for instance, at coins, they're used from rolled metal stock and they're punched, and you would have more of a situation where you'd have oriented phases and not perfectly random phases. But sometimes, like I said, we get lucky. But because of these considerations, we're always driving to try to get down to this smaller particle size. Now, how do we do that? Well, we use our muscles and we use a mortar and pestle. So the first basic equipment every lab should have is a mortar and pestle, because we're trying to get samples grind down to this fine dust. And that's shown here. And then the other important thing to have is a series of sieves, and sieves will trap the large particles, let the small particles go through. We want to get this fine fraction. And there's a lot of commercial sieves that will you can buy and get you different particle sizes. Now here's a sieve study where we actually took it through a series of size sieves to get down to our fine powder. But there's something important that I wanted to point out in this particular set of sieves is when you're at a larger size, like a couple of 100 microns or so, you usually can see the individual particles with your eye. And you can see colors in your eye, by your eye. And that's very useful. It'll tell you that there's at least 3 phases here. But the fact that you're seeing particles and particle shapes and colors means that the particle size is too big, because as you notice, as we go down in size, we're getting finer and finer and finer. And when we get down to this magical size below 74 microns, we have a powdered dust and you really can't see any definition in the crystals. And that's because your eyeball is a pretty good detector. Most people's eye can see particle and particle differentiation at about 25 to 50 microns. And that's the magical area where we want to grind our powders down. And so if you see particles with your eye, you're probably too large. And so you don't need a fancy instrument, you just need to have a critical eye. Now, once you get that powder down to a small size, you need to have things like spatulas, brushes, razor blades, and skimmers. And a camel hair brush is one I'd highly recommend. That's very good for moving this fine dust, packing it well in a sample, and creating a smooth surface. Now, this is also important because the smooth surface helps you with the noise, and the packing density helps you with a signal. You'll get more stuff per unit area. And since we all want better signal to noise, packing it well, getting a flat surface gives you a real chance of capturing a good signal to noise on your equipment and with the powdered specimen. So here's our absolute minimum checklist. You're going to want an agate mortar and pestle, series of sieves to get down to this smaller sizes, spatulas, brushes, safety razor blades. Now, depending on the field that you're in, there may be other things that you want in your lab. Hard materials, your arm is going to wear out before you crush it down to the fine size. If anybody's tried to crush down sand or quartz, they'll realize the problem. You can get real tired real fast doing that with a mortar and pestle. So a rock crusher with an impact hammer is a important thing to get. You get your particles, your pebbles down to a certain size, you put them into the cylinder, then you smack it with a hammer, it breaks it up to a fine powder that you can put and finish the job off in your mortar and pestle. And I've put rocks, pieces of cement, shells in there. You do have to get them down to the size of a pebble for this system to work. And to get them down to a size of a pebble, you may use something like a jackhammer or a giant hammer, or even dynamite if you're looking at a mineral formation. So you get it down to the pebble size. This will help you get it down to the powder size. Now, things that archaeologists and mineralogists also use is a pickaxe. I've also used things like lobster crushers, lobster picks, and dental tools. And that's because the lobster picks and dental tools are all hardened steel, fine picks. This helps you get a sample that you want that may be buried in a matrix. And recently I looked at an archaeological film and I laughed because the archaeologist was saying that he went to his dentist and asked for the dentist to use tools so that he'd have some fine picks to do his archaeological excavation work. And I went to a tool supply house instead of seeing my dentist, but it's the same thing. You're looking at things that can break apart hard things and then get you the sample that you want. Metals are particularly difficult. So to look at metals, many people will use something like a Dremel kit that has sanders, drills, metal brushes, because what you're trying to do is to get a fine metal, a series of metal fines that you can then put in your sample holder. A hacksaw can also be used. I've used hacksaw to cut up pieces so I could analyze them in a diffractometer. So super hard materials. You go in an opposite direction, usually with cultural heritage or pharmaceuticals. Oftentimes you have small samples They're highly precious. It may take you a lot of effort, particularly if you have a cultural heritage object, a precious painting, or a vase or something like that. You may want to take the smallest sample you possibly can so you don't do any damage to the particle. So this is where you use tweezers, something like an X-Acto knife, so you can isolate and find the materials you want to analyze. So depending on what you analyze, you may want to get these sort of tools as well. Now, if you don't want to use your muscles, a good thing is to have a laboratory mill. And I show you 3 mills. There's actually about 8 types of mills, but these are the 3 most common ones used in a laboratory. And we have a ball mill, an attrition mill, and a cryo mill. And how they differ is the amount of energy that they put into the particle during an impact. When you have a ball mill, you usually have very hard materials like stainless steel or tungsten carbide balls. You put in a lot of sample, the sample gets crushed between these balls, and that produces a lot of energy that can be used to cut down your particle size. If you want to lessen the energy, you use an attrition mill. In the attrition mill, you're changing the ratio. You're adding lots of media, very little sample, and that cuts down on the contact distance when these balls smash into each other, which lowers the energy. So this is intermediate in energy. This is high in energy. And then the lowest energy consideration is usually a cryo mill, where they're using the low temperature. Both may embrittle the sample, but it also will draw all the heat away as you're generating it in the milling process. Now, all 3 of these mills you can fine tune by your choice of media. And the general rule of thumb is hard media for hard materials, soft media for soft materials. If you use polystyrene to grind quartz, all you'll do is make a fine polystyrene powder, probably won't grind the quartz at all. But polystyrene might be a great media if you're looking at a pharmaceutical or a softer material. Agate, once again, would be used, or alumina would be used on your harder materials. So you have a basic energy range that each mill provides, and you can fine tune that energy range by your selection of media. Because what you're trading off here is you want enough energy that you break down the particle without putting in so much energy that you either cause a phase change or you're destroying the material. And so there's a balance. Other useful things to have in a lab is a drying oven. You want this up to 150 C so you can flash off any solvent or absorbed water. Sometimes it's helpful to recrystallize the sample, so you may want to put it in the solvent and then flash the solvent off. And if you have a drying oven, it's nice to have some accessories, which is usually a pipette, petri dishes, a microbalance that can get you down to 1 milligram. This is important because usually our samples are around 200 milligrams in size. That's a generality. They can range quite a bit. Usually if you can look at the sample and see a crystal, it's at least 1 milligram. And you might want to do some quantitative analyses or standard addition examples. So having a microbalance around and some weighing paper is a good thing. And finally, I'm going to talk about a radiation meter or dosimeter. This is to keep you safe. The badge is telling you basically when you've done something wrong and you've been exposed. The meter is probably more important because the meter can be used proactively to tell when there's a leak around your diffractometer. All modern diffractometers are designed to be sealed tight, but they get moved, they get bumped, particularly if you're in a multi-use environment. And it's really good to have your own meter because you can check that it's operating correctly and keep yourself safe. And another point I'll make here is if you don't have one of these in the lab, I would get one because you're responsible for your own safety. Relying on your boss or your management to keep you safe may not be the best thing. And if you don't have one of these meters, you should probably get them. Because of the wide use of medical x-rays, you can get these meters fairly inexpensively. And there's a wide variety of different ones you can get. Then we also recommend that in the lab, you have some of the Nist reference material standards to calibrate your measurements and calibrate your experiments. And you want to read these SRMs very carefully because they're designed for different purposes. We have 3 that are there for line position that gets you accurate and precise D-spacings, precise unit cell measurements. If you're doing phase identification, this is great. You can calibrate your D-spacings generally down to part per million type of area. The other thing that this does is the silicon and mica are both internal standards, and you can correct for specimen displacement. And this is the #1 error that we have in diffraction experiments. So this is handy to have in the lab so you can do some calibration. We also have a series that are line shapes analysis. This is good for refelt analysis to determine your instrument resolution, for crystallite size analysis to do the same thing. You want the right reference for the right type of measurement. I will mention the sintered aluminum plate. This is a external standard. It is a piece. So what you're doing with this piece is eliminating all the things that can happen when you make a powdered sample. And this is to look at your instrument performance as a function of time. You can tell, for instance, if you've changed your optics. You can tell if your tube is starting to fade because you measure this, use this piece, and you measure it at 1 day, 1 week, 1 month, 1 year, 10 years, etc. You can actually look at the performance of your instrument versus time, and that's the value of this particular standard. In quantitative analysis, it may be depending on what kind of things you're doing. Here's your respirable silicas. Alumina is used for the RAR method. So if you do some of those measurements, you might want to get that particular sample. So then we have this bigger list. And what I have in red is the equipment. What I have as black is most of the accessories that you want. But this is a general good list that would be common to any of those labs that we talked about. So do you need a fine powder? And the answer is no. But the fine powder does a lot of good things for you. It gets you that good packing. High bulk density gets you a smooth surface. Excellent signal to noise. You're reducing microabsorption and extinction effects. Extinction is double diffraction within a material, which means that you don't get the intensity coming out at the right area at your detector. It means your intensities are irreproducible. You can reduce your common errors, and you get the reproducible intensities that you need for accurate quantitative analysis and identification. Now, if you have a larger particle, all these problems come back into and can potentially plague your analysis. And some of these problems usually won't prevent you from identifying things. And there is one benefit. If you do look at a part or do look at something with large particles, you can identify and quantitate texture. So your goal may be to look at texture, and that's when you may want to use a large particle. These are all things I put in a diffractometer. You can see some are pieces, some are powders, some are films. All of them, I was able to get a phase identification. Some easier than others. On this acrylic paint, it was like rubber. I was having great difficulty making a flat surface. So the signal to noise on this particular piece was terrible. It was also pretty bad on this curved shell. And it can be bad on certain types of coin where you have large relief on the coin face. But we are able to get it in because you have your paints are fine powders dispersed in the polymer, and you can analyze both the polymer and the paint pigment. In these bottom stances, we were actually looking at the texture. We wanted to see how the shell was built. So we wanted to measure texture to find out how these platelets of calcium carbonate were oriented. In the coins, we were looking at whether the coins were cast or cut out a rolled sheet. That was part of our investigation in addition to the phase analysis. So these things were all analyzed with the hope of looking at the microstructure and gaining some information about the microstructure. We directly analyzed different spheres used in the pharmaceutical industry. The active pharmaceutical ingredient is actually on a microsphere. This is beneficial. You don't get any orientation, and actually this gave excellent data. In these tablets, we wanted to look at the surface chemistry, and we've actually got reference standards for the gels. So all these things work. It's just that you have to be a little bit more cautious when you know that you don't have a perfect 1 micron powder. Here's one of the more famous cases, but there's lots of examples like this. This is a gun. They were looking at the gunshot residue. They focused the X-ray right into this powder, got a great pattern, but the key was this pegboard sample holder that they made so they could put any solid object in the right path and focal spot of the beam. And then they could have an angular calibration. So they knew the relationship between the crystallography that they saw and the three-dimensionality of the object that they were looking at. And a lot of times, if I'm looking at a polymer film or something, this sort of stage where you have angular calibration is incredibly helpful. So there's many cases where it's almost impossible to get a 1 micron powder. And there's other cases where you don't want to do it. In the case of a pipe clog, they're usually the result of an insoluble material. They're often hydrates, carbonates, hydroxides. You do not want to change the chemistry. If you change the chemistry, you're going to change the problem, and you're not going to be able to solve and tell the engineers how to remove the clog. But you want to identify it as is. So you want to analyze the sample before and after any grinding treatment. In cultural heritage objects, you usually don't want to crush, pick, or grind them. It's not only that you might have a small sample or that they may ask you to analyze it non-destructively, but it could be that the sample is going to be used for multiple analytical techniques. So they don't want you manipulating it in any way. Explosives, it's very difficult thing to, you don't want to take a hammer to a shock sensitive material, obvious bad results. And if you get things truly down to 1 micron, you may be creating a hazardous dust. And the one I've bumped into many times is metals and non-oxides. You grind it, you make new surfaces, and they'll quickly exotherm in the air and oxidize with a lot of heat being released. I've actually seen this with a non-oxide ceramic where the heat was enough to melt a stainless steel reactor. So sometimes on some materials, you do not, it's a hazard to get down to small materials. So you get as low as you can, you test things before and after your prep, and then you go and do your analysis. So I'm going to just briefly cover some complementary techniques, and it will be very brief, but there are many times when you want to use the complementary method, particularly if you know you can't prepare it down to 1 micron, or you might have non-crystalline ingredients. And the two most common techniques are used are X-ray fluorescence and infrared for complementary techniques. Usually infrared is you're getting the organics at the same time. XRD is, or XRF is helping you with the inorganics. You can also use XRD for the inorganics and then compare, how does that compare to the FTIR results? That's most commonly used in cultural heritage and pharmaceuticals where you have mix of material. In geology, mining, earth science, you use XRF. And then you can look at the phases identified in the elements, see where you may be missing things. Maybe you have element in high concentration that you're not seeing in diffraction. That's usually a hint that you have to then start looking at amorphous materials and amorphous scatter, which is why this is a strong complementary technique. There's specialized complementary techniques. Catalyst ceramics are done at high temperatures. They're produced at high temperatures, so high temperature XRD, TGA, DSC is your complementary technique. Energy laboratories, cyclophotometry is used quite often, so they can look at materials under changing electric fields, which is usually things like charge and discharge of the battery. Metals, aerospace, and construction, usually you're looking at metals to take mechanical load, mechanical stresses. So often they're correlating to data from an instron or a load frame. These things can be combined. Once again, I'm going to go through this fast. This is a combination DSC X-ray, but in this particular pharmaceutical, it actually went through 7 structural changes. But the reason why you want to do that is there is a magical 20-degree area here where you get a single anhydrous polymorph. You've dehydrated the sample. You're before the temperature where you have solid-solid amorph anhydrous phase changes. So this is pretty critical information for an engineer that wants to make one form, either a reproducible hydrate or a single anhydrous form. And there's commercial units that are out there today. The one thing I haven't talked about is microscopy, and that's because this is what you should have in every laboratory. And that's because you get so much complementary information. Here's a picture. We know automatically, just looking at the picture, that we have 2 materials. One is a large particle, so that correlates to orientation in the XRD. The XRD can provide the specific orientation. It's telling you that the other phase in here, the alpha lactose monohydrate, is what this fine white powder is. Here we have another case where we had a a material we used in a pharmaceutical round robin where we had very large crystals that resulted in granularity. We told people in the round robin to grind them doing the standard sample prep, but some people still got these big grains. And so if you scanned along 2 theta, and here's the 0 point, so if we scan this way, you can see we get this intense, irreproducible peak in this one scan right here, and that's what you're seeing down here. So in this round robin, and if we have these pictures, we can explain exactly what's going on in these X-ray patterns, that it's a granularity effect. Some people got the right results because they did a good job preparing the sample, and other people got poor results. Here's electron microscopy on nacre, which is mother of pearl. And you can see it is a highly ordered material, but that's exactly what we see when we analyze this pen structure that is looking at the reflectance from the nacre right here. We see platelets, we get a size to the platelets, we get an orientation of platelets. All this data is perfectly consistent. Here's some inorganic examples when we're looking at different phases, different colors, different particle sizes. But basically what the power of microscopy and powder diffraction is you relate macro structure to microstructure to atomic structure. And that's why I would recommend you always have a camera in the lab. Depending on your price and your budget, you may have your cell phone, but versus an SEM, but always have a camera, always take a picture. So to conclude, we went through a list of basic equipment, the critical need to get a nice picture of what you're looking at, and other types of preparation equipment that you may need to get if you're working in specific fields. And with that, I'm going to stop and pass things over to Tom.
Great, thanks, Tim. Let me just get my screen going here and we'll start the next part of the presentation. All right, let's see what we got here. Okay, so to follow up here, we'll start talking about setting up your lab in terms of some concepts around the diffractometer, the database, and software. All right. So I'm going to be showing some examples of equipment, and the equipment that's demonstrated, it's not an endorsement of the equipment or the manufacturer. I like all of them, and they serve the purpose of demonstration for our presentation today. As this webinar will be made available after we are done with the presentation in a few days, I have included some references that you might want to look into, particularly for instrumentation and experimental techniques. Good references to go back and refer to for additional information. I always like to mention the concept of X-ray safety. Tim discussed the idea that you should have a Geiger counter, wear a film badge in your laboratory. This is an example of what happens when you put your hand in the path of an X-ray beam, and this is from an X-ray spectrometer. Excuse me. And with a very short duration exposure, you can see that there was lethal damage to the hand, eventually resulted in amputation. So just remember, the equipment is designed with safety features. Use those safety features and always be careful working in X-ray diffraction, X-ray fluorescence experiments. So the fundamental with the powder diffractometer is you have some type of a sample source, X-ray source. In this case, you have a sample stage, and then you have a detector. So from this cartoon, you'll see that the source, you typically irradiate a sample at an angle theta. It will scatter at an angle theta. So the detector is at an angle 2 theta from the direct beam. So you get a typical plot of your diffraction intensity versus that detector angle 2 theta. When you have the 2 theta angle, these peak positions can be converted to D-spacings, and this is telling you something about the unit cell parameters. The peak intensities tell you something about the atomic positions. The structure factor influences what the intensities are in your powder pattern. And then finally, the background tells you something about the crystalline amorphous content of your sample. So always look at the diffraction pattern to get a general idea of what's going on with your material. These are examples of powder diffractometers. These would be considered larger instruments, and by larger, we mean the radius of the goniometer from the sample to, or excuse me, detector to sample stage to detector. So you have your radiation source, stage, detector here, and different manufacturers design theirs, but the fundamentals are there. They generally the same concept. Again, as I mentioned, these are larger instruments, and two advantages. One of them in particular is that you get improved effect in terms of sample displacement, because the smaller the radius, the larger the effect of the sample stage, or the larger the effect of the sample displacement. The other I'll mention in a moment about attachments and advantage of those attachments on the larger instrument. Design of a lot of the new current instruments is that you'll see the source sample stage detector on what I will call the front side of the radiation enclosure, and on the back sides, the actual stage and motors where the instrument components are attached. You'll find that they're in some kind of a radiation enclosure, and typically it has a leaded glass so that you can see what's going on with the instrument but still be protected. You can buy a large number of attachments for these different diffractometers, and that's a flexibility option that's offered there, depending upon sample changers, put single capillaries, high temperature stages, tilting stages. The variety is very nice, and you can do a lot of different experiments using these larger instruments. Very popular today is the benchtop powder diffractometers. These instruments, as the name states, can sit on a typical laboratory benchtop. They have a much smaller footprint. The facilities requirements tend to be easier to deal with compared to the larger instruments. Primarily, they're designed for good phase identification and in many cases quantitative analysis applications. You don't have as many options when it comes to attachments. Some of the manufacturers do have sample changers, and a few have access to a high temperature stage. It's a moderate temperature, but you don't have the same flexibility as you do with the larger diffractometers. So a couple things to consider when looking at your diffractometer, the sample source and sample detector. So if we talk about laboratory X-ray sources, for most instruments, people will be looking at an X-ray tube. Some in the larger diffractometers may have the option to purchase a rotating anode. The main difference here is that you can have more current on the rotating anode, so you get a greater flux of X-rays. If you're doing micro diffraction or even single crystal work, you might use a micro source. Metal jet X-ray sources are now available that use either a gallium or indium anode. At modest temperature, these anode materials turn to liquid, and so you have a different cooling capacity need compared to a solid anode that you'd find in a tube or rotating anode system. And finally, there are laboratory synchrotrons that are available. These, of course, are very high end and usually used for high energy physics experiments. So we go from the X-ray tube, we say it's the lowest cost, up to the lab synchrotron highest cost. But keep in mind, your X-ray tube is still going to be several thousands of dollars when it needs to be replaced. The choice of radiation. Copper is typically used in powder diffraction experiments, and a couple concepts about why. When you look at a diffraction pattern, this happens to be for a calcium organometallic. 3 representative patterns that what it would look like if you used moly radiation, copper radiation or chrome radiation. With the shorter wavelength, the diffraction peaks all show up at lower 2 theta. As you get to the longer wavelength of chrome radiation, the peaks begin to spread out. I've put an arrow on a representative peak that is the same diffraction peak for the 3 diffraction scans. And you'll see that as I go to longer wavelength, the resolution improves. And you might say, well, then why don't I just use chrome radiation all of the time? There's another factor here, and that's called air attenuation. Air will absorb your X-ray beam, particularly your characteristic X-ray beam, and depending upon the energy of the radiation, that will influence how much air attenuation occurs. So in a goniometer setup that has a 20 centimeter radius, Moly has the highest energy and it has only about a 4% intensity loss. Copper, you'll lose about 33% of your intensity due to air attenuation. And chrome, you're losing 75% of your intensity just due to air. And so this is the balance between what gives me the best resolution and what's going to give me the best intensity. And this is why copper is typically chosen for most powder diffraction instruments. One exception could be if you are working with a lot of iron-containing samples. You're going to get a lot of fluorescence from the iron when you're using copper radiation. The K-alpha radiation is absorbed heavily and causes iron fluorescence. You might want to pick a cobalt X-ray tube. The cobalt K-alpha radiation is such that with its particular energy of about 6.9 keV, will not have a lot of the fluorescence issues due to the iron in your sample. There is a little more air attenuation loss than copper, 33% versus 48%, but it is a nice radiation to use, particularly if you have a lot of iron. And this is an example of a alpha iron oxide pattern. So just something to think about depending upon your sample type. The other thing that I want to just point out here, consideration when you're picking out your X-ray detector. The conventional detector is called a scintillation detector, a point detector, or 0D is a term that's used. Your sample, say, is to the right. The diffracted X-rays pass through some slits, and then it would impinge upon a monochromator that's at a fixed Bragg angle so that it diffracts into your scintillation detector. This type of setup does a point-by-point measurement. You scan, you might stop, count for a few seconds, step, few seconds, step, few seconds. And so it's a good detector, but it will take some time to get adequate X-ray diffraction intensity. What's currently available that a lot of people are moving towards are called silicon strip detectors, and they operate in what's called a 0D, 1D, and an approximately 2D mode. So this is probably a term you'll hear if you see someone talking about these detectors, and I'll explain these modes in just a moment. But the detectors have a solid state array. Essentially, it's a large number of silicon strips that are brought together. And the advantage is that they allow you to look at a range of 2 theta simultaneously. So you can collect data at a faster rate than the point detector, or if you use the same rate, you would expect to get better counting statistics. These detectors are excellent, they're very good, but they also are much more expensive than the point or scintillation type detector. You also have large area 2D detectors. These 2 flat detector versions can be put on your larger diffractometer goniometers. They cannot be installed on a benchtop unit. You have a special instrument here that uses an image plate detector that can be curved, so you maintain a pseudo Ewald sphere type geometry. And these particular detectors have the advantage in that particularly if you have oriented materials like this pattern I'm circling here with a beta polyvinylidene fluoride, The larger 2D area detector will allow you to see this preferred orientation much more detail than you can with a typical 1D type detector. Now, if I look at data from a true 2D detector, this happens to be aluminum oxide corundum pattern. And if I look at sort of what kind of data would I expect if I'm using a strip detector in what we would say is 0D mode. 0D is you would put slits over the detector opening so that you have a very narrow window here, just as you would in a scintillation detector. And if you then scan, you'd scan across your diffraction range, and compared to a true 2D detector, you'd see a small strip of that data. And this is what you would get out of the 0D mode. If you don't have slits, or at least you open up the slits over your detector, you now have a wider 2 theta range being viewed simultaneously. And what that means is that you have this wider detector opening, and you can collect over the same range as 0D mode, but you collect the data much faster. With this particular detector design, if you rotate it 90 degrees, you now are collecting a wider swath of the diffraction spectrum, and you can collect the data probably a little bit slower than in 1D mode, but certainly faster than 0D, and you'd get a bit more of the swath of the true 2D pattern. So the strip detector folks will convince you that this is in 2D mode. Just be aware it's not true 2D, but it does give you more information, almost like the old Dubai Sheriff film strip. Be careful though, because what you'll be shown when these detectors are advertised is someone can look at a pattern of gold, they can look at silver, and collect their data in a very short period of time, in under a minute. But that doesn't apply to all materials. Here's an example of a pharmaceutical that was collected in 33-second, almost a 3-minute, almost a half hour, and a 4.6 hour scan. And what you'll see, particularly when we compare the long time and short time scan, is that with the fast scan, yes, I have some data, but you notice it's very noisy data. I can't define my peaks very well. And the problem is I don't have enough counts to get good counting statistics. So do use some caution when you're told you can collect data very quickly with the strip detector. There are limitations depending upon the matrix that you're looking at. And ultimately, in this case, with this scan, using the very long scan, we were able to actually identify all of these phases in the sample, which you would never be able to do in that 33-second scan. On the other hand, you don't always need to have a 4-hour scan for every sample. And with a lot of the materials, you might be able to get by with just a few minutes, but understand the material that you're looking at. So when you're purchasing a diffractometer, here's some things to consider. What's 95% of the sample types that you're going to be looking at? Oftentimes I hear someone's asking a question, they're going to buy a new diffractometer for their lab, and they have a colleague who wants to do a low temperature diffraction experiment. And I ask the question, well, how many times a year are they going to want to do this? And when the answer is, well, maybe once, you probably want to find an outside location to do that experiment. You want to put your money into the instrument that's going to do most of your samples. Provide samples specific to what you analyze to the diffractometer companies so that you can see how does the data, how does the instrument behave when it's working with your particular materials. They're very good. These instruments are good, and they'll give you some data showing you analysis of different materials, but they're always materials that are selected that are single phase, good diffracting samples. Look at your materials. So when you consider buying the instrument, note what that performance was when you provided those samples. Does one instrument, 2 instrument, or 3 instruments all give you the results you're looking for? What is your budget? And the budget needs to include not only the diffractometer instrument, but your database and the software that you need. And we'll be talking about these in just a moment. What's your available space? The larger instruments need more space. Facilities, the benchtop instruments are simpler. They typically can plug into typical wall outlets. The larger instruments, you're going to need special wiring and special electrical needs and plumbing. Tim mentioned specimen preparation equipment. Make sure that you have that available because you want to prepare good samples. And one that a lot of people forget about is the maintenance cost. Do you need a maintenance agreement, which typically runs about 10% of the purchase price per year? Or are you going to repair this on your own? Will you be able to replace the X-ray tube when it goes out? Many times I hear of someone saying, yes, we have a nice diffractometer, but it's not running right now. And you ask why? Well, the X-ray tubes went bad. It needs to be replaced. And I don't have the $7,000, $8,000, $9,000 to replace the tube. So keep that in mind when you buy an instrument. All right, let's switch over to phase identification, where you're going to talk about database and software. So Tim mentioned about critical aspects of sample prep. You're going to collect the data, you get your diffraction pattern. You need a good database to identify the material so that you can get the qualitative and quantitative analysis. Powder diffraction file, there are 5 different databases depending upon your particular application. We'll be talking primarily about PDF4 Plus today, but each one has a different number of entries, a different number that has the atomic coordinates and applications. So think about what you want to do with your instrument, but the important part is that it is an editorially reviewed database so that you know the quality of the data that you are working with. PDF4 Plus does have the ICDD data. It also has ICSD data, the FIS database, some data from Nist, and it has data from the Linus Pauling file. So it's primarily inorganic, but it also has the principal organic phases that you need for qualitative and quantitative analysis. If your work focuses on organic materials, the PDF4 Organics database may very well be the appropriate one for you. In this particular database, we are, through our agreement with the Cambridge Structure Database, CCDC group, we do have CSD data in our organics database, and the, again, principal entries you need for quantitative analysis, Rietveld refinement, we have those entries with atomic coordinates in PDF4 Organics. So this is what the PDF entry looks like today. Some people will still call it a PDF card based on the old card technology that was used several years ago. You'll have your traditional D-space and intensity list, but it's flexible that you can calculate out the 2 thetas depending upon the radiation that you're working with. Many of the entries have the atomic coordinates, and so with that, you can do more than just the phase ID. The radiation sources we can work with include X-ray, synchrotron data, electron data, constant wavelength neutron, and time of flight neutron data. So we're very flexible in terms of which radiation source you use for getting your data. If we continue on with looking at that entry, when the atomic coordinates are present, you have multiple capabilities, including viewing the 3D crystal structure. You can, as I mentioned, simulate the electron diffraction pattern, backscatter diffraction pattern, and all entries you can simulate ring patterns to look at 2D detectors for analysis. All database entries, you can simulate a powder pattern, and many of our database entries now we're putting in the raw diffraction data, so you can compare your data to the data that was collected for this particular entry. The search form, which moves you now not only for doing phase ID, but also data mining, has many search features that you can use to be able to go through the database, find entries that are of interest to you, and extract what we would call materials characterization data. So with that, I'm going to give just a quick demo here. Here is the database with that opening search window. And as an example, if you're interested in manganese oxide entries, and so I only want to search the manganese and oxygen phases, I want those that have atomic coordinates. I am interested in phase types that are A2X3, meaning Mn2O3 type phases. And specifically, I want to view the cubic structured materials. So you have this capability of being able to do multiple search parameters to narrow down from the entire database to a small number that's characteristic for you. You can do a search, and there are 20 entries in the database that meet all of the criteria that I had input. You'll notice one entry here has a blue star by it. If you double click on that entry number, the PDF entry opens up, and that blue star under the experimental tab tells us the data were collected with an internal standard. So it means not only is it good data based on the quality mark, but with the internal standard, the precision is also expected to be very good so that you can have confidence in working with that particular entry. I want to point out something when you look at, for example, the simulated profile. You have the option to simulate the crystallite size of effect on the diffraction pattern. So we have a crystallite size viewer that as you increase the crystallite size, of course, you see your diffraction peaks will be narrow. And as you reduce crystallite size, you can see what the effect will be on the overall diffraction pattern. So it's just another tool available to you to be able to help characterize your materials. All right, so now I'm going to switch just for a second here to the JADE software. You've got the database, now you want to do the analysis. And there are two principal versions. There's JADE Standard and there's JADE Pro. JADE Standard is a perpetual license, and there are 4 options of visualizing your data, adding in phase ID, doing Rietveld, or doing the phase ID and Rietveld analysis. JADE Pro has all of the features of JADE Standard, plus additional capabilities, for example, cluster analysis. There's a toolkit with special features to do enhanced analysis of materials. It is a floating license, and it is an annual renewal, so you will also be getting annual updates. So let's do a quick JADE demonstration here. So you've collected your diffraction data. One of the nice things about using the JADE software is it is not instrument specific, so it can look at data from multiple instruments, multiple vendors, multiple sources. And the first thing that you can do is you will do your peak searching. You would look through the peaks to see, are you happy with the results? You can add a peak, you can remove a peak. You should be able to do that in any software that you're using. When it comes to the phase analysis, you want to make sure that you have a database loaded to do the phase ID. So you can decide on what subfile you want to search. So the ICDD databases are loaded here, and we're going to search the Linus Pauling file portion of the database, which is about 148,000 entries. Once you have established that component, you can then do your search match. And I've set mine up so that I will do what I would refer to as sort of a manual review. I'll show you in a moment about an auto approach, but I'm looking at the phases, and the first one that comes up is rutile, and I agree that that phase is there, so I'll say yes. The next phase identified is alpha iron oxide. I look at my pattern. Again, I agree with that. I'll say yes. And then the third one listed here is anatase TiO2, another agreement. And when I click on that, you'll notice in the diffraction pattern itself, there's sort of a little pink cloud there, and it says no remaining peaks found, meaning it has identified all of the peaks in this diffraction pattern, and I can feel comfortable that I have a 3-phase system. Okay. Once you have this, you can do a Rietveld or whole pattern fitting, and it will in fact now go through the phases that are there. You've identified them, and it will do your quantitative analysis. and you can get the information in terms of how much of each phase happens to be present in your sample. Now, this is the approach of that when you want to go through step by step. What has been built into the JADE software is what I would call smart analysis. And this is something that we've been working on for quite a long time. JADE is excellent in terms of this concept of smart analysis techniques, which we have something called one-click analysis. Once you're comfortable and you understand your system, you can click on the one-click analysis. It will identify the peaks. It will go through and do the phase identification. Upon completing the phase identification, it will do the Rietveld refinement for you, and the quantitative analysis is all done. So you'll see in a very short period of time, the full analysis is complete. You can even do things like look at the structures themselves that were identified to do more analysis of the particular phases identified. You can open up the structures. You can see that, in fact, what the atomic coordinates are. And now that you've identified phases, you can also take advantage of what we call the Mdi Toolkit. And with the Mdi Toolkit, there's enhanced analysis features, including, for example, the ability to look at stereographic projection. You can do tiling of the entries so that you can look at the unit cell, and as you rotate the unit cell and the structure around, you can see how it affects your stereographic projection. You can change your orientation. And so these are the tools that are all part of the enhanced analysis capabilities you'll find in JADE Pro. So let me finish up here.
Don't forget to like and follow ICDD on Twitter, Instagram, LinkedIn, and Facebook. More information on ICDD.com. Contact us at info@icdd.com.